Yeah, good morning all, and attendance is on, guys. Okay, is there a class going on right now? Anyhow, we'll wait for one more minute. Okay, fine. Let's like at least reach the 30 mark, and then we can start. Okay, so we have hit the 30 mark. So I think we can start now. Okay, so this is basically the last week and the last lecture. And let me just share it. Disappoint. Okay, so the whole point of this course was to give you some idea about modeling and design, right? And one of the ways in which people express their design ideas is UML, right? So one one of the major reasons for trying to look at UML from the perspective of designing was to learn some basics, right? Basics as in I do not expect that you guys will be able to create flawless UML diagrams. That was not really the intention. The intention was that at least you are now able to figure out that, okay, this is a sequence diagram, this is a class diagram, or this is an activity diagram. If you see it, at least you are able to identify them, because UML as a standard is too vast, to be honest, to be absorbed. Okay, sorry. Is the voice fine? I could see that my internet connection is fine. Any problems with others? Others might not even be listening. Uh, okay, okay. Um,
Fine, it's fine.
okay, fine. So yeah, Tia, there might be some issue at your end. Anyhow, so let's continue the discussion. So the overall idea is that at least at the end of the day, you should be able to identify, that this is a sequence diagram, this is a class diagram, this is a state diagram, and you at least have a basic understanding. It is not necessary that you remember all the notations, but at least you should know that if you are seeing a state diagram, what exactly does it represent? Similarly, if you are looking at a sequence diagram, how to interpret it. That is the overall idea. So this is basically the last leg of that essential UML, that I can call it, very elementary UML in some ways. So till now, you know that there are two aspects of a system that you are supposed to convey to someone else. Okay, the first aspect is the structural aspect. The structural aspect is basically the aspect which talks about how does your system look like, and the behavioral aspect is how does your system behave as in at the time of execution. So you by now you actually know that class diagrams contribute towards our structural understanding of the system. So you basically communicate to someone what are the different classes and how do they link, they relate to each other. So this is in some fashion a structural view of my system. The behavioral view actually tells me how my system will behave at the runtime, and there are some diagrams that you have already used: state diagrams, sequence diagrams, use case diagrams, activity diagrams. Use case, I'm not really sure what can I call it, behavioral or structural. It is kind of behavioral only, because use cases are something that your system is going to achieve at the runtime. So anyhow, so there are some diagrams that you already know about. There's maybe one more diagram that is quite common, and you might actually encounter it, especially when you see projects that span the boundaries of across multiple machines. Okay, so what I really mean to say here is that my system is not just a stand alone application that is running on just one machine. It is basically spread across multiple machines. That is what the idea is. So in such a case, what really happens is that I would want to communicate what elements of the system are present where. Okay, if I want to communicate this, then the allocation diagram in UML, or there is a general term for these kind of diagrams called allocation views. They are useful in disseminating this type of information. So the overall idea for an allocation diagram is to show certain boxes. These boxes, which are by the way different from the kind of boxes that you've been using till now. These boxes look like cuboids. Okay, so the idea is to show that they can contain something. Okay, this is probably the reason why we show them as cuboids. They are not rectangles but cuboids. So it's like they can house something. Something can go inside them. So these cuboid boxes are used to show hardware components, something like this, and then you can link them together with some kind of uh, connection. The connection part here shows how these different elements are going to communicate. So this is a typical example. In the previous few weeks, we have seen things like networking. So using the socket based networking, you can form a connection between any two machines using, so this is known as the TCP IP stack. Okay, so the two protocols that we used for communication were basically TCP and IP. So this diagram shows that there are three hardware components and they are connected to it via the TCP IP stack. Now the word hardware component or machine, it has become slightly obsolete now. Why? Because there used to be a time when the code was executed directly on a physical machine, but with the advent of virtual machines and cloud computing, now many a times your code really doesn't execute directly on a machine. Okay, it executes inside a virtual machine which might be running on a physical machine, or it might execute in a Docker container, for example, and then that Docker container might run on another VM, and that VM might be running on a physical machine. So now the overall concept of hardware has become slightly obsolete. Okay, so people take their liberty in displaying different types as cuboids. Okay, so for example, you might show a virtual machine or a container as a cuboid as well, or you basically can show a platform, like Google's Play Store as a hardware component, right, as a containing element. So people actually use their liberty to show these kind of elements. The idea is to show the containing relationship, that this is something where something else is being contained. So that is why you show that cuboid. And what exactly are you supposed to show in that cuboid? What exactly is it that you're showing these hardware elements? You're showing this because you want to express that there are certain software elements which are going to sit on top of them, right? And we call these software elements as artifacts. These artifacts could be something like a jar file. I know many of you may not have studied Java, but a Java application, when you create a Java application, one way to ship it from one point to another is through a jar file. A jar file is very similar to a zip file, for example. And then zip files are of course there. You can create a zip of whatever code you've written. You can directly create executables, like let us say like a .exe or something like that. So an artifact is basically some kind of a software deliverable that is going to sit on some containing element and then work and then execute. So you show that using a deploy connection. Okay, so you say that this particular software element will be deployed on this particular containing element, and you do so by using the deploy connection. And you can also use a number of custom connections if you feel that deploy is not really the right word. Okay, if you want to use some other word, there is a concept of stereotyping in UML. It is not just it is not just fixed to allocation diagrams. Stereotyping can be done pretty much anywhere in UML. And so what people do is they use these two symbols they look like, two less than and two greater than symbols, and then whatever you put between them, it acts like a kind of annotation, a kind of decoration for that, right? So you can do that as well. So basically this is how it looks like. This is an example of a ticket booking mobile application. So you create an application. Let us say it is an Android app. So usually the Android apps are distributed as .apk files. So you create a .apk file and then you put it on Google Play Store. Here I have not written anything. No, I should probably either write deploy or something. But I'm just assuming that the person who's going to see this diagram understand what it means. Okay, but here I have written the term deploy because it's a var file and it is slightly complicated. So what I'm trying to show here is this is the Amazon's. So Amazon has a cloud platform called EC2. We discussed EC2, I think, during ITP when some of you needed a virtual machine. So at that point of time, we talked about EC2 as well. But yeah, so what we you can see how I've chosen how I have taken up the liberty of showing something like this, a computer, and then within this I'm showing another cuboid which I'm calling as the server that is running. So this is the overall idea, that in a deployment diagram, the idea, the overall objective is to convey information about deployments, that what are the different places where the code that I have written is going to sit. And the idea is to simply communicate this to my stakeholders, the developers or the users, right? So you can see the example of custom connections here. So I say that whenever you actually install an application, what really happens is that the APK which is stored somewhere here, it simply migrates to your phone, and here it is installed. Okay, this is the typical process that happens. So instead of saying deploy, I'm just saying the only thing that is happening is it migrates from here to here, and then the app gets installed. So this is some convention that I have used. You can use your own conventions. The overall idea is to communicate. Any questions on this? We don't have too much content today, so we can afford to take some time. Okay, so you can of course go and have a look at this content later as well. By the way, if you in your project you are planning to build something which is going to run on two different systems, for example, then you could be benefited by creating a deployment diagram as well. But as I said, it only makes sense if you are going to have multiple elements, multiple containing elements. It is fine even if, for example, you have, let us say, um, a web server and a database server. Although people usually don't do that on the same machine, but the idea is you should have at least two elements for the allocation diagram to make sense. Anyhow, any questions? Okay. So now this is going to be the last lecture for the course. Hmm, where is that lecture? Close, open, recent. Yes. Share. Okay, so this is basically the last lecture of your syllabus, and this is some more system building stuff. There's like one more skill that I would like you guys to know about. Again, the whole idea of all these so-called system building skills is not really to make you an expert, because this is probably too premature for you to study. But this is about giving you an exposure to the kind of possibilities that are out there, so that if at all you require it at some point of time, you already know that there is something like this. Even if you don't know how to do it, at least you know there is something like this. So when you create a project, when you work as part of large teams, you know that there is something like this that exists. You can do this, by the way, right? So the last part of this series, this system building code series, is to look at what are shared memories and forking. So now remember that when we were working with threads, I used a term. I said that threads are essentially lightweight processes, right? And the reason I called them lightweight was because there was some kind of sharing between them, right? And it was the same process. So there was a common area, and these threads can share some data with each other. And we also saw an example where a global variable was being shared by two threads, and with the help of that they were doing some communication. Now, what if this was the case when you are talking about two threads which are a part of the same process? But what if you want to communicate across the process boundaries? Okay, there are two processes that are running, and or that may run at different times, and you want to use you want to communicate from one process to another. So then, what exactly can you do? So the most common way to do this is using a shared memory. Okay, a shared memory is basically a common block within your main memory, which is accessible to more than one process. Basically, it's like a free for all kind of thing. It's like a public space within your main memory where anyone can write anything and anyone can read anything from it. Okay, so a shared memory looks something like this. Now, in a typical scenario, what happens is whenever you create a process, some memory space within main memory is reserved for your process, and this memory space is basically exclusive for access to this particular process only. If, let us say, p2 tries to access a memory location which is part of this space, the operating system will not let p2 do that. Okay, it's kind of an access violation. And similarly, if p3 tries to access p2's space, that will be another access violation. So these are some of the checks that are done by the operating system to disallow any kind of what can I say, mischievous behavior. But in case of a shared memory, this is a block of memory within the main memory, for which basically the operating system takes off all the checks. Okay, so now as long as you know where this shared memory is, you can go and read it, or you can go and write it. Okay, it's like a public spot in a city. Whereas these memory spaces are like spaces of they are like your home, right? No one can enter your home without your permission. But a shared memory is more like a public park. Anyone can go, anyone can sit, anyone can come back, whatever you want, right? So the only thing that is required in order to access this particular memory is a key. Okay, so a key is basically a kind of identification. You basically say that this is my identification. I want to access this part of the memory, and then the operating system checks up it does some basic checking and says, okay, fine, you have the right key, and here is the location to the shared memory. You can go and do whatever you want with it. So let us say if process p1 wants to write some data into this particular shared memory, the only thing that this process need is the memory key associated with this shared memory. And this is good, because as long as you have the key, you can simply go and write it without any restrictions. And let us say the same key is shared with another process p2, so then p1 and p2 can communicate with each other. P1 can write stuff here and p2 can read, and then p2 can write stuff here which p1 can read. Of course, p1 and p2 should have access to the key. Both the processes should have access to the key. The major problem here is because the operating system doesn't really care. Okay, the operating system has basically said it's a free for all kind of scenario. Whomsoever want can come and access this memory. Because the operating system has stopped all kind of memory checks, any process which has access to this memory key can go and access this shared memory. Okay, so this is a kind of security risk that is there with shared memories, that if another process is able to figure out the key associated with your shared memory, it can go and violate it. And by the way, the onus, the responsibility of making sure that this key is only available to the participants which are supposed to have it lies on the developer. The operating system does not get into the way. It's your responsibility to make sure that no intruder gets access to the key. So now the question is, how do you basically generate this key? So this whole process of getting a shared memory and using it, it involves certain steps. The first step is to call the shm get function. Actually, it is not the first step. The first step is to generate the key, but the idea is that there is a function called ftok. What this function can do is you give it a string and a number, and it generates a key for you. The idea here is that the key has to be a long number kind of a thing, an integer, and it might be difficult for you to pass on this integer from one process to another. You have to manually send this to let us say the developer of the other process. So it is much easier to give a pass phrase and a pass number, right? So you decide that this is the pass phrase, it's kind of a password, and this is a number, and then this ftok function, if you pass this passphrase and a number, it will generate a key for you, which you can use to call this function, the shm get function. The shm get, or shared memory get function, can create a shared memory for you if it is not there, or it can provide you access to an existing shared memory. In both cases, you call the shm get method function. You pass on the key associated with that particular shared memory, and in the first case, when you're doing it for the first time, there is a flag, as in there is a parameter which tells the implementation that this is a new shared memory, it has to be created. But from then onwards, all the other calls, all the consecutive calls, do not need to provide this particular flag. You can simply go and access the shared memory. And after the shared memory gets created, please keep in mind that this memory does not belong to the process who created it, right? It is a general place within the main memory. So once the memory gets created, even the process which created it needs to attach itself. Attachment basically means that you are going to tell the operating system that I want to access this memory location. Okay, and if you do that, what will happen is that you'll now get an access to this memory via a pointer. Okay, a pointer is basically going to point to that location at the starting location of the memory block. And this pointer, by the way, is of type void asterisk. So you can typecast it to whatever form you want. By the way, when you create the shared memory, you have to provide the size of it as well, similar to malloc, that you say I need these many number of bytes. So in the same fashion, when you are creating the shared memory, you tell the operating system this is the amount of memory I need. The operating system simply creates a block of memory. It doesn't care what do you store there. Okay, so this shm80, the pointer it returns to you, it is of void asterisk type. You typecast it to whatever you want. Okay, and then use it whatever way you wish. Okay, you can use it like um, 10 bytes of characters, or let us say two integers and two characters. You can use it the way you want. One integer, six characters, it's basically 10 bytes. The way you want, you can use it, right? So people, you can also use it like an object memory. So you can say that I'm going to store an object here, an object or a structure variable, whatever it is. It is just a block of memory. Do whatever you want with it. And once you are done, you have done whatever read write that was required. After that, you just do the opposite of attachment. You basically you detach the process from that shared memory. And then the last step is to give the operating system an indication that this memory is now ready to be deleted. Now keep this in mind, that a call to this method shmcatl is not really going to delete the memory immediately. It is more of an indication to the operating system that this memory can now be deleted. The operating system will check if there are still any processes which are attached to this memory location. If there are, operating system will wait, and once the last process which was attached to this shared memory has either detached itself or it has exited, then the operating system at some point of time is going to delete that block of shared memory. Any questions on this? We will have a look at some code, but any questions on the overall concept of a shared memory? Okay, so there's one more thing, one last piece of code that is going to be there. And by the way, you guys know, right, that these codes are not going to be a part of your end semester syllabus. This is for your own knowledge. If you know these things, maybe it will be easier for you later in your B.Tech course. Uh, so the last thing that we are going to cover is the concept of fork. So what happens is something like this. Let us say you are having a thread of execution. I said the advantage of these threads is that these threads share data with each other, right? The common variables like global variables are accessible to all the threads. Now, in certain cases, that is certainly good because you can communicate between the threads. But in some cases, okay, you might not want it. Okay, in fact, what you may want is that whenever I create a new thread, I just want a separate copy of everything, including the global variables and everything. I don't want two threads to be able to share it, or I want the data to be manipulated independently. I don't want an actual collaboration here. And if required, I will use some mechanism to communicate. But for now, I just want it to be completely separate. For this scenario, you can use something known as this fork system call. Okay, so a fork system call will not create a new thread, it will basically create a new process for you. And this new process will be a replica of the existing process. So from wherever you call the fork, uh, the new process will become a replica of this from that point onwards. So all the variables and everything that were there in the parent process, there is a parent child relationship here, by the way. So the calling process, the process who called fork is the parent, and the process which now gets created is the child process. So there is a parent child relationship between these two, and the child is a replica of the parent, and the replica is done even of the data part. So all the variables that are there, they are also copied, okay, including the program counter. Okay, you remember what the program counter is, right? So let me give you a simple walkthrough. So let us say you have a code like this: PID equal to fork. What happens is that at this point of time, two processes exist simultaneously. Okay, right after this statement is executed, there are two processes now which are going to execute the next statement from here. So this if statement will now be executed by two processes simultaneously, not simultaneously, but you understand what I mean by simultaneously. It means multitasking, so time shared basis. So but from here onwards, this code will be executed twice. And now you might feel, what is the advantage of doing this? I'm just repeating computation, right? If it is a copy of the other process, how does it even make sense? So this is how it makes sense. Although all the variables and the code are going to be the same between the parent and the child, one thing is going to differ, and that is the value returned by fork. Okay, so whatever value is returned by fork, if I check it, I can figure out which of the two processes am I currently in. Okay, so if this value is, by the way, less than 0, it means that the fork failed. If the value is 0, it means that I'm currently executing inside the newly created child process. So in the child process, the value assigned to PID will be 0, and in the parent process, the process which called this fork statement first, it will be some positive value, which is essentially the process ID of the newly created process. So if you use this value returned by fork, you can do a bifurcation in the code. Okay, so everything that is added in this else if block, that will be executed only in the child, and everything that is put in this else block will be executed in the parent. Okay, so this way you can diversify the computation. So from here onwards, this way you can make sure that they are not really, even though the code is a copy, at the runtime you know that two different branches of your code will be executed. So this is a way to do a forking. With the help of forking, you can create a new process, and then this new process can execute some other code. Okay, so before we go to code, any questions on this, the idea of forking? You can of course go back, and I have also put the recorded lecture for this part, so you can of course go back and have a look at it. But any questions right now? Okay, so let me show you some code now. Okay, I hope you guys can see my virtual machine now. So let me start with the fork first. So here I'm using fork in a specific fashion. Okay, so this is my parent process, the process that I execute from the terminal, and then there is a call to fork here. Okay, so what I say is that basically the program counter is also copied. So any statement that will be executed right after fork, not at the C++ level, but at the level of assembly language, right? So the statement that gets executed right after fork will be executed in both parent as well as the child process. So what really happens is this particular function call is made. It has now given birth to a new child process, and this function call returns a value, which it is the same value that we catch in PID in the example that I showed. So now what I'm doing here is I'm going to check this inside an if condition. So this if condition will be checked in both the processes, the parent as well as the newly created child. And what does it check? It checks for it checks that whether this value is zero or not. Ideally, I should have put a case for less than zero as well, but for now, just assume that the less than zero part, when where the fork fails, that is not going to happen for our case. So then what will happen? I'm going to make a check on the return value. If the return value is zero, it means that this is the child process, and if the return value is something that is non-zero, it is the parent process. So if I put a not here, it means that the control will go inside this only in the child process, and the control will go here in the parent process. Okay, so now what I'm doing is within this parent process, I'm going to do another fork here, right? So now the parent has two children. The original parent, it has two children, and then within this code again, I have put the same thing, if not fork. So um, here I'm going to come here only in the case of child process. I'm not going to come in case of the parent process. Okay, so now what is going to happen? Basically the newly created child can is going to fork two more children like this. So there are three levels of forking here, two levels of working. Actually, the original one is let us say the L1 process, and then it gives rise to two L2 processes, two level 2 processes, and then each level 2 process also gives birth to two level 3 processes. So now you have four more new processes. So you can see the kind of tree that is getting created here. If I run this, uh, this is what it says, that there is one L1 process. It has the process ID 10765. Then there are two L2 processes. They have the process ID 10766 and 10767. And then each of these two L2 processes, they actually spawn two more processes. So now you have four L3 processes. and they have the IDs like this. Okay, so this is the idea of what is forking. Please keep this in mind that fork can, um, if you're not doing it with caution, there can be so many forks, because at each step the process gets duplicated. So the code that is written right after that point, the fork point, that will be executed twice. Okay, so it is possible that if you write fork followed by another fork, then the second fork will be executed in both the processes, the parent as well as child. So it might actually give rise to more processes than you wanted to. You probably thought that giving two forks will give rise to two processes only, but it will give rise to an additional process as well. So keep this in mind. Whenever you want to use fork, use these if and else conditions, so that you are sure that you are doing exactly what you are supposed to do. Any questions? Sorry. Mhm. So any questions? Okay, so then let me also show you one last thing, the shared memory. So here I'm creating a shared memory. I have some data that I am going to put in the shared memory. This is my data. And now I have, as I said, right, I need to create a unique key. And this unique key has to be shared with all the processes which are interested in communicating with this so-called shared memory. So how do I do that? To do so, I use this FTOK function, and I give it a pass code and a pass phrase, right? So now this is why it is easier, right? Instead of sharing an integer value or long integer value, I can now share a pass phrase, which is easier to remember also, and a pass number, and then these things can be converted into a unique key. And then this unique key, by the way, this function is guaranteed to give you the same output as long as its two inputs are the same, right? So if the same input is used in another process, in another program, the key value will be exactly the same. So now once I have this key value, what I'm going to do is I'm going to call the shm get. Here, this is the flag IPC underscore create, which says that a new shared memory should be created. And these are some access control things, like this is similar to the Linux access control, right? If you guys have used it, 7, 6, 1, 4, those kind of things. So this shm get function, it creates a new shared memory and returns an ID associated with this shared memory to you. Now, if this value is less than 0, it means that the shared memory could not be created. But if it is a non-zero value, if it's a positive value, then basically the next step is now to attach this program to that memory. To do that, you just pass on the ID that you got from SHMKit. You don't need to worry about this for now. And then what really gets returned is a void asterisk pointer from this SHM80. You can now typecast it to whatever pointer you want. Right here, if it is a long, it will be 8 bytes. Here I provided, by the way, the size of the shared memory. I provided it here. So I'm saying please create a shared memory for one long data type. So it will be probably 8 bytes. And so then I using this pointer, I'm just going to typecast this as a long asterisk thing. And then all I have to do is use it like a regular pointer. Like a regular pointer, I can assign it values, or I can use it to read the value at that particular location. So here what I'm doing is I'm assigning this data to that so-called shared memory, and then I simply write that this is the data. Okay, and then after doing all this, I'm going to detach myself from this memory by providing that same memory pointer. And you can see that I'm not deleting it as yet. In this process, I just wrote something, and I detached myself. In the other process, The initial part is exactly the same. You need to generate the exact same key that was used to create the shared memory, and you can do that using FTOK. Then you can call the SHM get. This time you don't need to provide the IPC create. You simply give the size and everything else, all the other information about the shared memory, and you get the ID. Here the same thing, you are going to attach yourself with that shared memory, and here I'm going to read from that shared memory. Okay, so I'm going to read the data from that shared memory place, and then I'm just going to show this is what I read, and then I detach myself. And since my job has been completed, I make a request to the operating system using this IPC underscore RMID flag that please mark this shared memory for deletion. So if I do this, you know that I already wrote that value using the first process. If I run this, so I did something wrong. I did not run the code, I guess. Run me first. Now the code has created the memory, and now you can see. So it is good actually. I had not executed run me first. Okay, so that is why it says failed to find the shared memory. So then I created the shared memory, then I ran it again, and now it is able to read from the shared memory. Any questions on this? Again, don't be worried about the details. Just uh, just understand that there is a concept of a shared memory, with the help of which, if you have two independent processes, you can communicate with each other as long as you have the common shared key. Okay, any doubts, any questions? No? Okay, so if you have no doubts, this is it for object-oriented methodology. You can go and have a look at the content for the last 3 weeks again, and you can send your queries to me over email. But yeah, this was the last part of the syllabus. Thank you. Any other questions? Last questions? Any? If are there any, I can take. Otherwise, we will break. Okay, guys. Then thank you.